Hello. In this video, we'll introduce another way of comparing two different signals. So in the last video, we know that we can compare two signals by their expected utilities, right? To see if any of those signals is giving a higher utility than the other one. So in this video, we'll try to see that to find another way to compare the signals and to see how the informativeness is really compared here. Okay. All right. So recall that we have in our example, right, from the last video. So we give another name. So we call that as pi. So in this example here, we have two pi's. So we just name the previous pi as the pi a. Okay. Okay, so pi a, remember that we have, if the state is omega 1, then we have the probability of sending S1, so we call this as S1a, which is the probability of 0.9. Okay, so otherwise S2a is 0.1, right? So similarly for omega 2, S1a is 0.3, and the probability for sending S2a is 0.7. Okay, so this table is for the distribution over the signals given different states, right? So here we are trying to give another example and try to compare those two different signals. Here we name this as pi b. So again, we have those probabilities. Here we have S1b and S2b respectively. So we just give another different probability for the different probability of sending the signals if the state is omega 1. Okay, so we just give it 0.6 and 0.4 as an example, but we keep the same as the lower low here as 0.3 and 0.7. Okay, so the example is just as this. All right, so remember that we have already calculated the posterior beliefs, right? So we just write them again here. For the pi a, we have mu omega 1 S1a, it was 3/4. Mu omega 1 S2a, this is 1/8. Mu omega 2 S1a is 1/4. Mu omega 2 S2a, it was 7/8. Okay, so correspondingly, we can of course calculate those posterior probabilities or posterior beliefs for the second signal pi b, right? So we just skip those steps and I'll just show you the results. Omega 1 S1b, which is 2/3. Mu of omega 1 S2b is 4/11, right? So those are just calculated by using the base rule, right? Mu omega 2 S1b is 1/3. Mu omega 2 S2b is 7/11. Okay. All right. So, and we also have our total probability of sending S1a, in this case, is 0.6, and this is 0.6. Okay, and pi S2a is 0.4, of course. So correspondingly, pi S1b, we can get this, which is 0.45. Pi S2b is 0.55. Okay, so those are just some very simple and straightforward calculations that we can do for those two signals. Okay, so remember that in our last picture, okay, this is the utility, right? And this is the belief prior or posterior beliefs of omega 1. Okay, so remember that we have this little square. Okay, suppose this is 0.5. Okay, we have those diagonals as the expected utilities for those two different actions, right? Okay. Okay, suppose this is a quarter, so this is 1/8. Okay, so we have for our first signal, right? Our prior belief is redistributed with a distribution over the posterior belief, right? So this is the prior belief at 0.5. So 1/8 is one of the posterior belief, and another one is 3/4, right? Right here. Okay. So this was distributed, or it was splitted to those two posterior distributions, two posterior beliefs, right? Okay. So correspondingly, we have those expected utilities in the picture, right? So previously, it was 0.5 as the expected utility. So later, after the signal is presented and is sent to this decision maker, then the expected utility is increased to this point, right? Okay. So remember that this point has a 0.8 expected utility, and originally it was 0.5, right? So this is the value of the first signal of the pi a, right? Okay. So how about in this case, in our new example here, for the new signal pi b, okay, we use another color. Okay. So we have our 2 points of the posterior beliefs. So one of it is 2/3, right? Here, suppose. And another point is 4/11. Okay, all right. Okay, so we connect those lines, and suppose that we have those crossing points here, and we connect those 2 points, and we get this value. Okay, and actually we can calculate this value, right? So it's not hard to calculate. Let's do that. So the expected utility in this case is 0.45, right? We have this probability of sending S1b times the corresponding posterior belief, which is 2/3, plus 0.55 times 0.55 times the actually this is the 1 minus 4/11, right? Because we're calculating the expected utility rather than the posterior belief, right? So this is simply get from the picture by using the 1 minus this number. So it's the straight line, right? So this is very simple to get this, and so this is 0.65. Okay. All right. So this point is 0.65. So it means that in this case, this interval or this value, this gap is the value of the pi b, value of the second signal. Okay. So we can see that the first signal obviously has a higher value of signal, or the value of information structure, than the second one, right? Pi a has a higher value than pi b. Okay, so this, in terms of the expected utilities, now we can use this to actually help us to compare two different signals, right? So we're comparing signals using the expected utilities, right? Okay, so that's the first way or first approach that we can use to compare two different signals to see which one has a higher value, right? Okay, so that's the first approach. So next we're going to try to introduce the other approach, the second one, and to see that to see which signal brings more information. Okay, so here we call this concept as as a garbling. Okay, so in this case we call that pi b is a garbling of pi a. Okay, so this is this term is very straightforward because that pi b here, right? So we can see from this table here. So they have the same probability here for the omega 2, but for the omega 1, obviously pi b, it has a more centered distribution for the omega 1, right? Compared to pi a. So in this case, pi b is sort of a garbling of pi a. So it kind of mixed, it has a more mixed distribution, or it doesn't, it has a less information than pi a in this case, right? So if we look at pi a, then we know that the omega 1 has a more diverse or a more spread distribution than the case in pi b, right? So this is the meaning of this garbling. So here we mathematically define that. Okay. So a garbling okay. So here pi b, which is a map from the state space to the set of all distributions over the space of the signal realizations for the pi b, right? So SB here. So this pi b itself is a garbling of pi a. Okay, so if there exists a function gamma, which is a map from SA to delta SB, okay, such that pi b can be written as gamma pi a. Okay, so explicitly pi b SB omega. Okay, so correspondingly it can be for all those for any omega, right? The probability or the signal of sending SB can be written as a probability that the signal of pi a, right, times the corresponding gamma function. Okay, so here have the gamma SB given as a, right, and times pi a as a omega. Okay, and we sum over SA, right, for all the SAs. Okay. All right. So this intuitively, right? So this is very similar to the signal processing, right? So there's a in the field of engineering, right? So we say that this omega, we call this as the state, but in their field they call this as the signal. Okay, so they don't mix those things up. So here the omega is the unknown variable, right? Is the state of nature in our models. So we have this omega, right, and we have our pi a initially, right? So if this omega goes into our pi a, okay, and then it sends out S1a, right? Okay, so what's a garbling of that, of a pi a, is that we have this gamma function, then this S1a goes into our gamma function, and it sends out S1b, okay? So actually, this is not the only approach or the only path, right? So pi a, it also sends out, let's say, S2a, right? In our example here. So this also goes into gamma, and then gamma outputs this S1b, right? So together, actually, they have all those results, right? So if we want to have our output from gamma for our S1b, then S1a and S2a, they are all the inputs into this gamma function, right? Okay. All right. So here, alternatively, so we can actually regard this whole picture as something more simple. Okay, something simpler. So here we have the state omega. Okay, and if we can actually combine all of those into our pi b, right? And then it outputs our S1b. Okay. Of course, this will also output S2b, S2b, right? Okay. All right. So this is just a straightforward, a simple visualization of that. Okay. So we need to rigorously derive those how we are using this gamma function to calculate our garbling, right? As the pi b as the garbling of pi a. Okay, so now let's do this. Okay, so remember that we have, okay, so actually we can write this pi b, right, S1b omega 1 as, okay, so here we just put a question mark, right? So we don't know if we can do this or not. So let's just assume that we can do this. So we can write, perhaps we can write this as follows. So gamma S1b S1a pi a S1a given omega 1, right? So this is one possibility that given that the state is omega 1, then this pi a sends out S1a. Then given that S1 is S1a, right? So given that the given S1a, then there's a gamma function to calculate this conditional probability of the S1b, right? So that's the whole path here that we're calculating this part. Of course, there's another possibility is that gamma S1b given S2a, right? So this is also possible. So correspondingly, here should be pi a S2a given omega 1, okay? So here is S1a and S2a, but this is omega 1 and omega 1, okay? All right, so similarly, we can also do this for S2b, right? So let's do that. Okay. So this is S2b, right? All over those places. S2b S1a, pi a S1a, omega 1, gamma S2b, S2a, pi a S2a, omega 1. Okay, so those are very similar things. And also we can change our omega 1 to omega 2, right? So let's just copy and paste this. Okay. All right. So we change all those omega 1 to omega 2. Okay. So that's it. Omega 2, omega 2. Okay. All right. So you can see that this is actually just a system of 4 equations with 4 unknowns, right? So this is S1b, S1a. Okay. So this is S1b, S1a. Okay. This is S2b, S1a. This is S2b, S1a. Right? And this is S1b, S2a, S1b, S2a. And this is S2b, S2a. Right? So those 4 equations, they just have 4 unknowns. So perhaps we can solve that. Okay. So now let's do that. Okay. So this is 1, 2, 3, and 4. Okay. So we simply plug in all those values, right? So the number 1 becomes 0.6 equals gamma S1b given S1a times 0.9 plus gamma S1b S2a times 0.1, right? So this is the first. So the second becomes 0.4 equals gamma S2b given S1a 0.9 plus gamma S2b given S2a 0.1, right? They have the same signals here. Number 3, 0.3 equals gamma S1b given S1a times 0.3 plus gamma S1b given S2a times 0.7. Number 4, 0.7 equals gamma S2b given S1a 0.3 plus gamma S2b given S2a times 0.7. Okay. All right. So now we can solve those, and we can first combine 1 and 3 together, right? So we use 3 times 3 minus number 1. So this becomes 0.3, right? Equals 2 times gamma S1b given S2a. So it turns out that this is gamma S1b given S2a is simply 0.15, right? So that's straightforward. Then we plug this into number 1. And so we can just get this gamma S1b. So we plug to number 1. So gamma S1b given S1a will be 0.65. Okay. This is not hard to calculate. So similarly, we use number 4 times 3 minus number 2. Okay. So similarly, and then we can get gamma S2b given S2a is 0.85. And then we plug this into number 2 to get gamma S2b given S1a is 0.35. Okay, so now we have all those results, and we can actually write them together, right, in the matrix. Okay, so pi b is 0.6, 0.4, 0.3, and 0.7. Okay, so this is omega 1, omega 2, and this is S1b, S2b, right? So for the pi a, this is S1a, S2a. Okay, so this is simply 0.9, 0.1, 0.3, 0.7. Okay, so those are just the examples. Okay, and our gamma, right, we have already solved those. Gamma is that so 0.65, 0.35, 0.15, and 0.85. So this is S1b, S2b, S1a, S2a, right? Okay. All right. So, and we realized that actually pi b is the multiplication of pi a and gamma, right? So this actually equals to this times this. Okay. And we can see that each row here, they also add up to 1. Okay. Right. So this corresponds to the stochastic matrix or the Markov kernel. Right. So since the inverse of this matrix, actually it doesn't exist, right? It exists, but the values, they're not valid, right? So they're not in the unit interval. So we can see that pi b is a garbling of pi a, but not the other way around, right? Okay, but pi a cannot be a garbling of pi b, right? Because we cannot solve a valid gamma for that, right? Okay, very good. So now we have known two different ways, right, of comparing the information structures, right? So, okay, two ways of comparing the information structure or the signals. So the first one is to use the expected utility, right? Or the second is to use the garbling, right? So pi b is the garbling of pi a. So in this case, pi a has a higher expected utility than pi b, right? So those two are the equivalent approaches for us to compare the different information structures to different signals. And this equivalency will actually be proved in a well-known theorem called the Blackwell informative theorem. Okay, and they also provide another condition or another approach in addition to those tools. Okay, so later we'll show the Blackwell informative theorem and try to after we show the third approach or the third condition or the third method to compare different signals. Later, after that, then we can actually really show the Blackwell informativeness and its theorem and try to prove the equivalency, right? Okay, so that's pretty much about how we use this idea of the garbling to model the to compare the informativeness between two different information structures or different signals. Okay.